Hey everyone! So in this video I like to talk about filling out tables and finding equations that fit or match with these tables. So let's start with this example here. We're given a scenario where it says that Binyam plans on sharing an apartment with 3 other friends. And so below we have a table showing the rents of different apartments in the area and what Binyam's share of the rent would be. Right, so if we look down here at this table, we see that when the total rent for the apartment is $1,600, Binyam's share would be $400. And when the total rent for an apartment is $1,800, Binyam's share would be $450. And so here we have a few missing entries. And let's take some time to try and fill out these missing entries based on the previous information in the table. So here, maybe take a moment, pause the video, see if you can think of how these values are related to one another, how you might get from 1,600 to 400, or maybe let's say 1,800 to 450. What's the pattern here? And so it seems like the rent is split evenly across the 4 people in the apartment. There's Binyam and his 3 other friends. And in this table, it looks like the pattern seems to be that we're taking the rent and dividing it evenly across the 4 people in this apartment. Right, 1,600 divided by 4 is 400. Maybe another familiar example is 2,000. If we take that and we divide it by 4, that's 500. And maybe these examples seem a little bit less familiar, but 2,100 divided by 4 is 525. And so it feels like the relationship between the rent and Binyam's share is that they're just taking the rent and dividing it 4 different ways, splitting it evenly. And Binyam would pay 1/4 of the total rent. And so here, if we want to fill in the rest of this table, all we have to do is take these rent values and divide them by 4. So we would take 2,200 divided by 4, and this would give us, this is also probably not one that's very easy to compute in your head. Feel free to use the calculator, that's okay. But it's also good to get a sense of how numbers interact with one another. One way I would think about this is that there's $2,200 that they're splitting 4 ways. Maybe it's easier just to think of the first 2,000 part of it. If I were to split that 4 ways, each person would pay $500. And then there's still $200 left over to split 4 ways. And 200 split 4 ways is 50. So that'd be 550 that each person would have to pay for. So 550. So that goes in here. And we can do something similar to figure out that 2,500 divided by 4 is equal to, well, I know that 2,400 divided by 4 is 600. And then there's still $100 left over to split 4 ways. And so that would be fair if everyone would pay $25 to account for that missing or remaining 100. So this would be 625. Of course, you could do this with the calculator. I just think it's beneficial to get a little bit more number sense and practice thinking about how you would divvy up these numbers. Okay, so that's how we filled in the rest of this table. Maybe let's take a moment to try and write an equation that relates the rent and Binyam's share of his portion of the rent. Actually, maybe we can sort of do a little preliminary step. So we figured out if we have these rent values, what Binyam's share of the rent would be. We would just take that value and divide that by 4. And so if we just found some apartment for Binyam and his friends, and there was some amount of rent, how would we compute Binyam's share of the rent? Well, we would just take whatever number that is, our variable rent, and we would divide that by 4. That would be Binyam's share of of the total rent. And so, that's really the idea behind building an equation that sort of represents a situation, or that would go along with this table. Right? So if we wanted to write an equation for Binyam's share of the rent, well, the idea is that Binyam's share of the rent we can compute that by taking the rent and dividing it by 4. Really, this is a representative equation for the situation above and for the table. And maybe just to take this idea and extend it a little bit further, we talked about variables, and we talked about representing variables with a letter, right? So oftentimes variables will be replaced in shorthand notation with a letter. And if we want to do that, we really want to state explicitly what that letter is representing, what it means. And so maybe in this situation, we might call rent, we might label it with the variable R, right? The total rent for the apartment that they're trying to all stay in. And we might replace the variable Binyam's share of the rent with the letter B, right? So maybe we can let B represent Binyam's share of the rent. And we can use any letters we want to represent these variables, but oftentimes we'll try and use letters that are very representative of the ideas that we're using or we're talking about. And so R and B feel pretty natural. And so using these letters R and B in place of our variables, our equation above would become B is equal to R divided by 4. And we can also use a fraction bar to represent division, so maybe you could also see this as R over 4. These are the same ideas. So for this next example, I have 2 tables here, and I would like to do 3 things for each of these tables. So the first thing I'd like to do is identify a pattern or a rule that is true for all of the pairs in that table, and then use that pattern or rule to fill out the rest of the table. And then lastly, take your pattern or rule and rewrite it as an equation. And so here, maybe let's start with this first table. And I would encourage you to pause the video and see if you could kind of think through any of these problems yourself for this first example. But one thing I'd like to mention before you pause the video or get started is that, our previous example, our variables were very explicitly stated. It was the rent, the total rent for that apartment, and Binyam's share of the rent. Here, we don't see the variables, we don't see what they describe, but we're given letters in place of the variables. But that's okay, the same ideas still hold. Let's try and identify a pattern or a rule for this first table between each pair. And so, you might have noticed this, but if you look at this value of M here, how could you imagine getting the corresponding value for G? Maybe you would think one idea is, well, 6 is twice as much as 3. That's true. And you might try and see if that pattern applies to the other pairs. And if we look at the next pair, 5 and 8, well, that's not true, right? 8 is not twice as much as 5, and so that rule is not really, or that pattern is not really true for the whole table. And so that's not really what we're looking for to go along with this table. That's not going to help us find an equation for this table later. But another way we can get from 3 to 6 is through addition by 3, right? Add 3. And if we look at the next pair, this rule also applies to this pair, right? So if I go from 5 to 8, well, that can be seen as adding 3 to 5, right? If I take my value of M and I add 3 to it, I get my G value 8. And we can go through all the other pairs and see that this is true there too, right? 2 plus 3 gives us 5, 10 plus 3 gives us 13, and we would see here that if we take 12 and we add 3 to it, you get 15. Right, so that would be the corresponding g value for an m value of 12, given what we know about this table. And then for 16, if we add 3 to it, well, we get 19. And for 18, if we add 3 to it, we get 21. So here, if we look at the tasks we were asked to complete for our table, well, we for the first table at least, we identified the pattern or the rule that is true for all of the pairs in that table. We filled out the table. And the last thing we want to do is we want to write our pattern or rule out as an equation. And maybe to make this a little bit more explicit, if I have some value for m, what would we do to this value of m to get our corresponding value of g? Well, we would take m, whatever it represents, and we would add 3 onto it, just like we did for all of the other examples. And this would be our corresponding g value. Right? And so what that means is that g is really the same as, or can be obtained by taking our value of m and adding 3 onto it. G is equivalent to m plus 3 when we look at this particular table. And so that's our equation for this table. All the pairs in this equation satisfy that, all the pairs in this table, if we take their m value and their g value and plug them into this equation, they would make this equation true. The left side would be the same as the right side, would come out to the same value. So let's take a look at this next table here and try and apply the same ideas. Let's try and find a pattern or a rule for the whole table, and let's try and fill out the table and come up with an equation for this table. So here, I can look at this pair here and try and come up with a rule to get from 4 to 16. One rule that might come to my mind is, what would I need to add to 4 to get 16? Well, I would need to add 12, right? But if I try and apply that rule to other parts of this table, right, 5 and 15, well, that rule doesn't work, right? 5 plus 12 does not give me 15. 2 plus 12 does not give me 18. So that's not the valid rule for this table. What about, how else could I get from 4 to 16? I can get there through multiplication. Right, so here, if I try to multiply 4 to 4, I would get 16. And maybe that rule might work for the other values in this table, but if I take 5 and I multiply that by 4, I don't get 15 either. So multiplication by 4 isn't a valid rule for this table either. Well, maybe we can try subtraction now. What could I subtract using 4 and get 16? Well, I can subtract 20 by 4 and get 16. Right, well, maybe we can apply that same idea to our other parts of our table. What if I take 5 here and I subtract that away from 20? Well, then I also get 15 here, right? Or if I take 2 and I subtract that away from 20, well, I get 18. And if I take 0 and I subtract that away from 20, I get 20 as well. And so, the rule or pattern we seem to have found here is that we take our value of t and we subtract it away from 20, and that's how we get our value for w. Right, and I would encourage you to pause the video. That might be a mouthful or a lot to take in, but I would encourage you to pause the video and check that this is really true for all of the values we've tested so far, all the pairs we've tested here so far. Is if we take our value of t and we subtract it away from 20, we'll get our value w. And so what would that mean the corresponding value of w would be when t is 6? Well, here we would take 20 minus 6, and this would give us 14. And what about for when t is 10? Well, we would take 20 minus 10, and this would give us 10. And then in this last example, if we take 20 minus 12, well, this would give us 8. And so, actually, in case I didn't make this clear enough, we can really showcase this for some of our other examples above. If I take 20 minus our t value, 20 minus 4, we get 16, or if we take 20 minus 2, we get 18, right? 20 minus 0 is 20. If we take 20 minus our t value, 5, we get our w value, 15. Right here, this is really the case where these values are t and these values are our w values. And so in general, for whatever value of t we choose, our corresponding value of w we would just take that value of t away from 20. That would be the corresponding value of w. And so that seems to be the pattern here. And how would we write that in, in an equation form? Right, the idea is that we could find w by taking 20 and subtracting away our t value. That is the equation for our table. And so this was kind of a messier or more challenging pattern or rule for this table. And I should also say that not all tables will have a pattern or rule or equation, but if there is one, it's nice to find it. And sometimes they can also be maybe a little bit more complicated or hard to find. So in this next example, we're given a situation. It says that Maria plans on asking for a raise at work, and she wants to make an informed decision about how much she should ask for. And so to help her out, she wants to know how much she will earn at the end of an 8-hour shift at different hourly rates. And so let's fill out this table so she can compare these earnings. And so here we're given this table where one of the variables is the hourly rate. And so here we're given different values for that variable, and it's given the letter H. We want to examine an hourly rate of $13 per hour, $15 per hour, $15.50, $16, $17, and some arbitrary amount of hourly rate, H. And so we want to compute the corresponding earnings she would get at the end of an 8-hour shift. And so let's start with this example 13 here. So if she works 18 hours, not 18 hours, if she works 8 hours and she's getting paid $13 per hour, well, how much would she earn? We can imagine computing that by taking 13 and adding it onto 13 8 times, right? Here this would be 13 plus 13 plus 13 plus 13 plus 13 plus 13 plus 13. I think I would need one more. I think this would be a total of 8. Right, so how much would this come out to be, right? $13 for each of those 8 hours. This would come out to be $104, right? So this is 104. That would be her earnings at the end of an 8-hour work shift if her pay was $13 per hour. And then a more direct way of computing this is, I hope this is very explicit and clear why this is a valid way to compute the earnings, but a more direct way to compute this is 8 times 13, right? Multiplication is just a way of saying repeated addition, right? 8 times 13 is just a way of computing 13 added to itself 8 times. And so this is really the same as multiplying 13 by 8. And this comes out to the same 104. And so really, if we want to compute her earnings at the end of an 8-hour shift, we just need to take her pay and multiply it by 8, right? Her hourly rate added to itself 8 times is really the same as 8 times her hourly rate. And so if I'm going to take, right, so here maybe I should say that this is 8 times 13. And so if I want to find her earnings when her hourly rate is $15, I just need to take that quantity, 15, and multiply it by 8. And so here, what's 15 times 8? Or 8 times 15, either way works. We get the same value. 8 times 15, this would equal, what would this equal? So here it might be beneficial to use a calculator to get the answer, 120. We'll definitely talk about more ways we can compute this without a calculator, but it might be helpful to have some tools later on in the class before we really dig into this kind of nitty-gritty computation. Here, if we go to $15.50, if we want to multiply this by 8, we end up with $124. we take her hourly rate of $16 per hour, at the end of an 8-hour shift, adding 16 to itself 8 times, or multiplying 16 by 8, we end up with $128. And then this last example, if we take 17 and we multiply by 8, we get $136. And in general, if she just handed us some hourly rate, we would compute the earnings by just multiplying that hourly rate by $8 or 8 times, right? So this would be 8 times H in general to compute the earnings. And so, if we wanted to come up with an equation for Maria's earnings based on her hourly rate, we would just say that her earnings, E, right, we've defined that earnings with the variable E, this is equal to 8 times her hourly rate, H. So in all of the previous examples, we've taken a table and we've built an equation from that table, but we can also go in reverse. If we were given an equation, we can fill out a corresponding table for it. Right, so here, the idea is that we have a relationship between this variable C and this variable M, and it says that we can compute values of M by taking values of C and multiplying them by 3 over 2, or 3 halves. And so here, let's fill out this table below and find some corresponding values of M. Right, so here, if C is equal to 0, what is the value of M? Well, what we do is we take our equation, say M is equal to 3 over 2 times C, and in this case we're saying that C is equal to 0, right? So this is 3 over 2 times 0. Well, 0 times anything is 0, so here this comes out to be 0. What we're really saying is that M is equal to 0 when C is 0. And then we can do the same thing for when C is equal to 1, right? M, we want to figure out what M is when C is 1. So we're saying 3 over 2 times C, but in this case C is 1. And well, 1 times anything is going to give you the same result, right? Multiplying by 1 doesn't really do anything. And so 3 over 2 times 1, this is 3 over 2. And so M is equal to 3 over 2 when C is equal to 1. So here this is 3 over 2 is the corresponding value of M when C is 1. And we can keep going with this, right? Here, if we let C be equal to 2, we would just multiply 3 halves by 2. And now this is a little bit less clear, right? How do we multiply fractions again? Well, when we multiply fractions together, we multiply numerator to numerator, denominator to denominator. But this really only makes sense when we're multiplying one fraction with another. But here we can rewrite 2 as a fraction because 2 is the same as 2 over 1, right? 3 over 2 times 2 is really the same as 3 over 2 times 2 over 1. Because here, if we take any number and divide it by 1, we just get that number back, right? 2 divided by 1 is still 2. Right? These are really the same. There's no difference between what I've written here really and what I've written here. Okay, and so now we can apply our idea of fraction multiplication. We can multiply numerator to numerator, denominator to denominator. We get 3 times 2 over 2 times 1, which is equal to 6 over 2. And then we can reduce this fraction, right? Fractions can be reduced by dividing out the same number from the top and the bottom, right? So here, if we divide by 2 from top and bottom of this fraction, we get 3 over 1, which is just 3. So this is 3. And so, I want to talk about, in a moment, maybe a slightly cleaner way of doing this. There's a lot of steps in this, and maybe a little bit of unnecessary steps in this. But let's just compute a few more examples first, and then I'll come back to that idea. So here, if we have C is equal to 5, well, we can compute M by taking the same approach, right? So replacing C with 5, we would rewrite 5 as 5 over 1, because 5 divided by 1 is still 5. There's no difference between what we've written between these two different parts of our long equation. So here we get 3 over 2 times 5 over 1. We just multiply straight across. We get 3 times 5 over 2 times 1. And this is 15 over 2. And now this doesn't reduce. 15 over 2, there's no common quantity that we can divide the 2 by. So that's just our result here, 15 over 2, and that's okay. So here I just want to make clear that when we multiply two fractions, we multiply numerator to numerator, denominator to denominator. This is really only true for multiplication. That idea doesn't really work for addition or subtraction. If we want to add or subtract two fractions, we need to make a common denominator. But here multiplication for fractions is very nice. We just multiply straight across. So let's do this one more time. For c is equal to 6. So we take 3 halves, multiply by 6. So 6, maybe I'll jump ahead. I can rewrite 6 as 6 over 1. And this gives us 3 times 6 is 18, over 2 times 1 is 2. And here we can reduce our fraction by dividing out 2 from the top and the bottom. Right, there's a common factor of 2. They're both divisible by 2. And this gives us 9 over 1, which is just 9. And so here we got some nice clean answer, just like we did in the previous example, or the previous example. Right? There's no denominator in these two examples. And why is that the case? Well, here, one way you can interpret multiplying by 3 over 2 is you can see this as first multiplying by 3 and then dividing by 2. Or dividing by 2 and then multiplying by 3. It's the same idea. And so when we looked at c values that were even, well, if I take 2 and then divide it by 2, well, we're just going to get 1, and then multiplying that with 3, well, that's just going to come out to be the 3 that we expected here. Okay, so the fact that this was even meant that it was going to be cleanly divisible by this 2, and this result would come out as a nice, clean whole number. And that was the same as what happened here. And so here, when we take 6, we can view that as 6 divided by this 2. And that gives us 3. And then what's left is, well, we still have to multiply it with this 3. And that gives us 9 out. Right, so here, multiplying by the fraction 3 over 2, that's the same as multiplying by 3 and dividing by 2. And so when we divide by 2, 6 divided by 2 is 3, and then 3 times 3 gives us 9. So that's just getting a little bit comfortable with fraction multiplication. And so we were given some values for c here in this table, but of course we could add more pairs of our own, right? So we don't have to be limited by just the values we were given. We can pick our own and make more pairs for this table. And so maybe just to give you a few examples, if we take 10 for c, we can find our corresponding value for m. Maybe just to do one more, we would take 3 over 2, and that would be multiplied by 10. And like I said, this is the same as dividing by 2 and then also multiplying by 3. And so when we divide by 2, well, that's really going to give us this 5, right? 10 divided by 2 is 5, and then multiplying by 3 gives us 15. Okay, so here that's how we can take an equation and really make a table out of it. We talked about graphing in the last video, and I'd like to continue that conversation a little bit. Just get a little bit more practice and familiarity. So, in our table here, we had c for our first variable for our left column, and m for our second variable, our right column. And so if we wanted to form a graph from this table, well, we can make our horizontal axis correspond to that first variable. So here our horizontal axis, and that can go with our variable c. And then our vertical axis can go along with our second variable m. And so what we can do to graph out our table is we can plot the points in our table and sketch the curve that goes through all of our points. Right, so let's look at one pair. And so let's plot this point. So this point says 0 for C, 0 for M, and together that forms this point here. Actually, maybe I'll do this in black. Right, this is the point that when we look at its position in relationship to the c-axis, well, it's at the 0th position on the c-axis, and if we look at this point's position at the m-axis, it's also along the 0th position. Here maybe we can pick a more explicit example. Here if we look at this pair 2 and 3, 2 for C, 3 for M, how will we plot this point? Well, we want a point that, relative to the c-axis is in position 2, and relative to the m-axis is in position 3. Well, here if we look above the c-axis at 2, at this point, notice that along the m-axis it has a position of 3. So this is the point that corresponds to the pair that we had earlier, 2 for C, 3 for M, is this one single point. Because when we look at the c-axis, it's located at 2. If we look at the m-axis, it's located relative to, it's at that 3 along our m-axis. So again, I want to emphasize that it's not two separate points here, 2 for C and 3 for M. It's really one point, so that when we look at the c-axis and we look at the m-axis, we get those corresponding values 2 and 3. Okay, so let's keep this going. Here, if we look at, maybe let's do the nice numbers first, 6 and 10. So 6 and 9. So 6 for C. And 9 for M. So 9 for M is located here. And so this is the point corresponding to a C value of 6 and an M value of 9. Let's do two more. Let's also do these not nice ones that include a fraction in them. So 1 for C and 3 halves for M. So 3 halves is 1.5, right? So this is 1 for C and 1.5 for M. So that's here, right? If I look down to my c-axis, it's at 1. If I look down to my m-axis, that's 1.5. And then one more. We're at 5 and 15 over 5, or 15 over 2. So 15 over 2, that's 7.5 if we wanted a nice clean fraction or a decimal to have an idea of what number we're looking at in our minds. So 5 for C and 7.5 for M. That looks like here. So right, 5 for C, and I'll stop at 7.5 for M. So that's this point here. And so if we sketch a curve through all of these points here, we get something that looks like this. Not so much of a curve, it's a straight line actually. And here I'm going to draw this little arrow at the end of it because, here, like we saw, we could keep going and add more numbers to this list. And so we can make this set of points as long as we want and go out as far as we want, and it seems like the pattern would be that it would just fall on this straight line. Right, so here, because we can make this list as long as we want, it would really go on in this direction forever and ever and ever, and the graph, this line that we drew, really goes on past this grid. So we want to make that very clear when we draw out our graph. And actually, it goes in the other direction too, infinitely as well. And so this is the graph of our table, it's the graph of our equation above, and so here that's just a little bit more practice with that. And one thing I really like to mention is that it was very important for us to identify that the graph is a line here, a very straight line here. It was important for us to actually have our axes labeled in a very evenly spaced manner. So what I mean by that is, like, if we were to draw a graph, a grid to sketch a graph, if we were to label our axes, here it's labeled 1, 2, 3, 4, 5, 6. If these were not spaced evenly apart, we wouldn't really be able to draw an accurate conclusion with this kind of grid. And so here, whenever you're sketching out a grid to draw a graph, you want to make sure that your axes are they're labeled in a very consistent and even way. This is very important so that we can draw accurate conclusions about the data.